Hi, I'm Farzaneh Abazari, postdoctoral fellow at University of Saskatchewan. Today we are talking about origin attribution of RSA public keys. This work has been done in the Cyber Lab at the University of Saskatchewan. Secure communication on the internet is becoming a norm. Nowadays, nearly 90% of internet communication is encrypted. However, several studies pointed out weaknesses of cryptographic protocols like TLS, SSL, SSH, and HTTPS. The majority of these studies investigated insufficient security of generated keys as a main reason of the problem. These problems are due to weak random key generators and the lack of entropy, improper implementation of cryptographic libraries, and pure misuse of cryptographic algorithms. The first study in this field has been introduced by Svenda in 2016. They identified the probable origin of a key based on combination of implementation decision made in software libraries in the presence of a certain hardware. This work has been extended by Nemec in 2017. They showed that it's possible to attribute individual keys to a group of similar libraries. The weakness of previous works is the necessity of identifying misuses such as weak implementation decision that effectively lead to a bias in a produced key. However, our approach tries to extract features that are completely independent of knowledge of the originating library, underlying platform, and the operating system. So, in this research, we want to answer this question that if it is possible to identify an exact origin of an individual cryptographic key, in another word, we want to assign a key to one of these major libraries. In this work, we focus on the RSA as an algorithm that is most popular in security. RSA is based on two large prime number. Based on these two large prime number, we can calculate modulus, and the exponent value and D value, that is one of the component of private key, can be calculated based on the modulus value and P and Q. Then the pair of exponent and modulus will form public key, and the pair of D and modulus will form private key. Here you can see an example of an RSA key that has 1024 bits line, and you can see that for P and Q, that are two prime components, for each we can have 512 bits. Then we can calculate modulus and exponent and the D value. The overview of the attribution approach is illustrated in this figure. First, the generated keys are decoded and parsed to derive the modulus. Then we examine the characteristic of key modulus to find out if there is any kinds of pattern inside. Then, after we extract the features, we can use classifier to attribute keys to the original library. To validate our approach, as we talked in the previous slide, we need to generate different set of keys. We use 4 cryptographic libraries to generate these keys. These libraries are listed as OpenSSH, OpenSSL, GNU-TLS, and GPG. We also use 9 Linux distributions released over the past 11 years. To ensure the sufficient entropy for key generation, we enable software-level random number generator and hardware-level random number generator. For software level, we use Havaged, and for hardware level, we use TrueRNG and NeoG. Keys that were generated in the first phase all has 2048 bits because this is the minimum key size recommended by NIST to be used in an RSA algorithm. All modules are unique. In order to check the value of component, if they are prime or not, we use Miller-Robbin test. And in order to check the randomness of the moduli, we use NIST statistical test that's composed of discrete Fourier transform and money-bit test. For the first test, we want to detect any periodic features in the moduli, and for money-bit test, we want to check the proportion of zeros and ones for the sequence. After we perform this test, we see that number of keys that pass these tests are more than 98% of the keys. In this step, for each key, we want to consider numerical and textual representation of a modulus and derive features that quantify its randomness and its spatial characteristics. For the numerical features, we use bin position that determine the preference of the library in choosing a modulus within a specific range. We also use two compression algorithms called Brotli and LZMA to measure the degree of randomness. We also use Shannon entropy to measure the entropy. The next set of features are textual features that tries to first we present the modulus as a sequence of bits. Then we calculate the longest repeated substring. We also look for sequence of ones and zeros. And the last but not least feature is mirror pattern. That in these features, the modulus binary string is represented as two halves of equal size. We then perform a comparative analysis of the n-bit pattern found in the first half versus the n-bit pattern in the second half. And in the first experiment, as we talked, we generated 6.7 million keys with different cryptographic libraries and with different versions on different platforms. The first figure shows the accuracy of attributing a key to the source library. That means one of the four libraries that we have discussed before. The best average classification accuracy that we got is 75% for with random forest, logistic regression, and neural network. In the second experiment, we want to show the attribution of each key to the corresponding library version. As we can see here, we can attribute with random forest with 85% accuracy. I think this is for GPG keys. So for GPG keys, we can attribute 85% of keys to their origin library version. For OpenSSH, we can do this with around 70% accuracy. And for the of other libraries, we have smaller accuracy for attributing keys to their origin library version. In the next experiment, we analyzed the release node for each library. Then we aggregated the library version that involves any changes to random number generation process. We want to see if changing in the implementation of the cryptographic library has any effect on the keys and the randomness of the keys. For example, in OpenSSL 1.1.1d, we can see that the accuracy of attributing each key to this corresponding library version is 93% accurate. This is because of OpenSSL library version 1.1.1d came out with a completely rewritten random number generator, which in turn resulted in 93% of the produced key to be positively linked to the specific version of the OpenSSL. In the next experiment, we want to attribute keys that we collected in the wild. We contacted 220,000 publicly reachable IP servers on port 22 and 2222. We make a single connection to each host and request their public SSH RSA key. This table shows that the majority of keys, around 155,000, were generated using OpenSSH library, which is known to be one of the most widely used SSH libraries of the internet. We are able to attribute keys to their originating library and its version. We can see that the performance ranges between 68% to 100% accuracy. For those result that we have we have a 0% accuracy. This is because of the lack of sufficient data. We try to run the experiment with different set of features in order to see which set of features has the most impact on the accuracy we got. As we can see, for all features, numerical feature and textual features, we get somehow the similar accuracy. The best accuracy we got is 95% for all features and all textual features. And in order to reduce the number of features, we try to do the experiments on one feature, two feature, and the top 5 features. And you can see that by choosing only these set of features, these 5 set of features, we can get 78% accuracy. That is a high accuracy compared to the 95% accuracy for around 14 features. To better estimate the accuracy and efficiency of our solution, we have decided to compare the performance of our source attribution approach to the performance of the model developed by Nemec. We have therefore implemented and applied their approach on the set of our generated keys. That means the set of 6.7 million keys. As we can see, the highest accuracy with this model is 42%. That is much lower than the accuracy we got. The practical implication of this project or research is that with the knowledge of specific library reversion, attackers can simply target library-specific attacks. And also the presence of predictable patterns in the keys that we have proved can be leveraged to expedite the factorization process, so the attacker can access to the component of modulus faster than before. The general expectation of cryptographic is that produced key shouldn't bear any sign of the originating library. So we cannot assign any key to the originating library. However, we have been able to positively associate a percentage of the collected and generated RSA keys to a specific library and also to a specific version of such a library. The validation set that we use is 6.7 million generated keys that has been generated on with 4 different cryptographic library on 11 platforms. 75% of the keys can be attributed to the origin library, and also in each library, in average, we can attribute 85% of the key to its version. Then we employed our approach on a collected set of key that we collected from the internet. So we got the accuracy around 68 to 100% to attribute keys to their library version. Thank you for listening to this presentation. Please feel free to contact us if you need any more information.